The key in here, back with another Ultra-Scale Playbook video, which is episode 10, I believe. So it means a lot to me that we've got to episode 10. I hope that if you're watching this up to now, that you'll be able to take a lot of good insights and valuable GPU programming lessons from this. Let's not waste any more time. Context parallelism. So we talked about T, tensor parallelism, and SP, sequence parallelism. And these methods allow us to reduce GPU requirements significantly. However, when training models on longer and longer sequences, in other words, when scaling to 100,000, 1 million tokens, we might still exceed the memory available on a single node, as we still have to process a full sequence length when we're inside the tensor parallelism region, because we are not splitting along the sequence length, we're splitting along the head dimension length. Moreover, even if we use full recomputation of the activations, which comes at a heavy compute overhead of 30% extra, we still need to hold in memory some activations at the layer boundaries, which scale linearly with sequence length. This point is kind of strange because if we do complete recomputation of activation, then we don't need to hold anything at the layer boundaries. That's only to improve or reduce the computation bottleneck. But anyways, all we need to know is that activation recomputation does come with a large throughput downgrade, like it makes it slower in essence. And then let's look at this graph for the memory usage of an 8 billion parameter model with no parallelism, TP2 and context parallelism 1, and then tensor parallelism 2 and context parallelism 4. So this is for 8 billion parameter model, so not really that big, but you can still fit almost, I guess you could fit a 32,000 context length model on a setup with only 2 GPUs. So tensor parallelism 2 means that we have 2 GPUs, and that's not that bad. Now let's get into this section where we say that the core idea of context parallelism is to apply a similar idea to the sequence parallelism approach. That is to say, splitting along the sequence length, but to the modules where we already apply tensor parallelism. So in the tensor parallelism modules, we're only splitting along the head dimension in order to have the intuitive conception of splitting the heads such that in the multi-head attention, each head is split up into its individual head. And however, we're also going to split along the sequence length now. And we will split them, therefore, in 2 dimensions, reducing the effective sequence length. And we're going to see how this approach works. There's something that you need to pay attention to, though, with respect to the attention. I blanked out this paragraph because it's just redundant. But now let's look at this. So it says splitting the sequence doesn't affect most modules like the MLP layer and the layer norm, since they are token or sequence independent, which is to say that no matter the order that you pass in the sequence, it gives the same output. And this is also the reason why, for example, in a regular feed-forward neural network, it does not perform as well on an image recognition task because it does not have the spatial awareness of where the pixels are, whereas in a convolutional neural network, because of the 5x5 kernels, or however large the size is of these kernels, then you do have the positional awareness. So that's a little tangent, just to say that the MLP and the layer norm layers are sequence-length independent, so we don't really have to worry about any complications with applying context parallelism. But when we get to the attention blocks, there is one important exception, because the attention in the attention module, each token needs to access the key value pairs from all other sequence tokens, or in the case of causal attention, which means mass attentions, at least attends to the previous tokens. So attention will definitely have a more complex calculation scheme inside of context parallelism, which will be explained both by an example, or rather through a graph, a diagram. So you will see this in an intuitive sense. Okay, context parallelism splits the input along the sequence dimension across GPUs. The attention models will require full communication between GPUs to exchange the necessary key value data. That is to say, since attention requires all of the sequence data and it's going to be split across the GPUs, well, therefore the GPUs will have to communicate with one another. And this does sound expensive if we do it naively, but there is a way to do this in an efficient way, and it's called ring attention. Now let's move on to this note, which says that context parallelism shares some conceptual similarities to flash attention, which we'll see later in the series, as both techniques rely on online softmax computation to reduce memory usage. While flash attention focuses on optimizing the attention computation itself on a single GPU, context parallelism achieves memory reduction by distributing the sequence across multiple GPUs. So in the sense of whether it's a distributed or a single GPU regime, this is what distinguishes flash attention from context parallelism. And now let's talk about ring attention. Oh, scheiße. In this implementation of the attention mechanism, each GPU instantiates an asynchronous communication operation to send its key value pairs to the other GPUs. And while waiting for the other data to come, it computes the attention score for the portion of the data that it already has in memory. And ideally, the next key value pair is received from another GPU before this computation finishes, allowing the GPU to start the next round of computation immediately after it finishes its current computation. And to illustrate this, we'll have 4 GPUs with 4 input tokens. So each GPU has 1 token, and Q1, K1, V1 will represent the query key and value matrices of the first token. I guess it's not a matrix, it's just a scalar value, but there's really no concept of attention for a single token. So it's kind of just an analogy here. And the attention calculation will take 4 time steps to complete. At each time step, each GPU performs these 3 successive operations. So you'll have these 3 operations times 4. So the first thing that it does in this set of 3 operations is send the current keys and values to the next machine, except during the last time step in a non-blocking manner. So we can start the following step before the current step is finished. And I believe a non-blocking manner just means that they're not sending them so as to cause like interruption and interference, but that's just my guess. Step 2 is locally compute the attention score on the current keys and values it already has, which typically involve doing the scaled dot product attention, which is the softmax of QKT divided or scaled by the dimension of the attention heads, and then you multiply by the value matrix. And then in step 3, we essentially wait, or ideally, like it said, the keys and values from the previous GPU would already be there, and these were sent in step 1 to the next GPU. And then we perform these 3 steps 4 times to complete the attention calculation with 4 GPUs. So here we can see in this animation the 4-step cycle where we start with the GPU having Q1, K1, and Q1, and then it starts cycling through, noting that the query matrices stay with each device, and the keys and the values, which are the KV cache, is what is rotating between the devices. So in essence, it's just a ring trade-off between all of the GPUs. And then on the last step, we of course do not send it back because that GPU would have already computed the attention score for its own key and value matrix. And here you go. This is why it's called ring attention, because it looks like a ring. But there's one big problem, which in a naive implementation of ring attention leads to some strong imbalance between GPUs. And this is due to the shape of the mask used in causal attention, which is to say that every single word only attends to previous words, because if you can look forward in the context, then during inference time, you will have a weird bias where at training time, you could look ahead of you, but when you're actually making words, well, you can't look ahead because those words have not been made. So this is why causal attention is only allowing tokens to look back for context. Let's look at the attention score matrix to understand what this means for a distributed setting. So you can see here that the GPU imbalance has the first device doing little work and the fourth device doing a lot of work, and the first device being able to compute immediately, but the fourth device having to wait until I guess the 12th token is generated, or I guess in training, no, this would not make a difference because all of the tokens are already loaded, but I'm more thinking of inference time. So just ignore that. The softmax is computed row-wise, which means whenever a GPU has received all the tokens of a row, it can be computed for that row. And we see that GPU1 can immediately compute it as it starts with tokens 1 to 4. And GPU1 actually doesn't need to receive any information from other GPUs because of causal attention. However, GPU2 will need to wait for the second round to also receive 1 and 4, and thus have all values for tokens 1 and 8. Also, GPU1 seems to perform much less work than all other GPUs, as it is only computing attention for the 4th, 3rd, and 2nd and 1st token, which only look back to those respective tokens, whereas the 16th token has to look back to all of the 15 past tokens. Now let's see if we can do a better way of distributing the GPU task. And of course, there is something called zigzag ring attention, which I think is just an amazing name. And this distributes the input sequences better. And this is achieved by assigning the tokens not purely sequentially to the GPUs, but by mixing the order a bit such that we have a good mix of early and late tokens on each GPU. So the attention mask will show an even distribution of computation. So now that if you count the number of colored squares, you'll see that computation is a balance across all GPUs. So it's kind of alternating between them. You can see GPU4 has the middle, GPU1 has the beginning and the end, and it's more balanced. At the same time, we'll see that in order to complete all rows, each GPU will need information from the other GPUs, of course. This is what we established with communication, since you require all attention score values in order to have a complete attention matrix, then there is communication necessary between them. And we have 2 general ways to overlap computation and communication, either by performing a general all gather here, regrouping all the key values on each GPU at the same time in a 0 reduction optimizer type way, 3 type way, or we gather them one by one from each GPU to each GPU as needed. So this is the first method and this is the second method. I can't really intuit this myself because I haven't really seen the code, but I think it's only really necessary to have a high level understanding of this unless you really would like to understand ring attention deeply. And once again, the key difference between these 2 implementations lies in the communication patterns and the memory usage. So in the first implementation, all GPUs simultaneously gather the complete key value pairs from all the GPUs in the all gather activations. And it requires more temporary memory as each GPU needs to store the full KV pairs at once. And communication happens in one step but with a larger memory overhead. Whereas in the second paradigm, which is one by one. GPUs exchange KV pairs in a ring-like pattern, one check at a time. It's more memory efficient as each GPU only needs to store one additional chunk temporarily, and communication is spread out and overlapped with computation, though with some additional base latency overhead from more communication steps because it has 3 versus 1. Overall, the all-to-all approach generally offers better memory efficiency at the cost of slightly more complex communication patterns. So let's say the all-to-all is the second option, while the all-gather approach is simpler but requires more temporary memory during the attention computation, since we need to store the full KV pairs at once at this all-gather step. And we've now seen how we can split a model across one node with tensor parallelism to tame large language models, and adding context parallelism to tame the activation explosion that occurs with long sequences that scale quadratically. However, we still know that tensor parallelism doesn't scale well across nodes. So what can we do if the model weights don't easily fit on one node? Well, we have another degree of parallelism that is the fourth so far. That's called pipeline parallelism, and that's what we'll be discussing in the next video. I think everybody has seen what pipeline parallelism is like this, and if you've seen a DeepSeek implementation, it's much more convoluted than that. So in the next video, be prepared to challenge yourself.